Assistant Professor Dr. Siddhartha Chattopadhyay sir. Dr. Chattopadhyay sir is an assistant professor of IIT Kharagpur Department of Humanities and Social Science. Sir was the visiting faculty of Binod Gupta School of Management, IIT Kharagpur. He was a former instructor in the University of Albany State University of New York. He also served as a research assistant at the Center for the Studies and Social Science, Calcutta. Sir completed BSc in Economics from Calcutta University and completed MA in Economics from Delhi School of Economics and University at Albany State University of New York. Sir has also completed PhD in Economics from University at Albany State University of New York. Sir has research interests on monetary economics and applied econometrics. His interest in teaching also includes subjects like macroeconomics, international finance, banking theory and practice, and econometrics. Sir has published 9 papers in the field of economics and 7 papers in the interdisciplinary field in referred journal. Sir has also published 3 book chapters along with 2 other publications and 7 working papers. Sir has teaching experience in Binod Gupta Group of School of Management, IIT Kharagpur, Department of Humanities and Social Science, IIT Kharagpur, and University at Albany State University of New York. Sir has also completed 6 projects and supervised 2 PhD theses. He had won many awards, honor, and fellowship in the area of teaching and research. He has also been an editorial referee in many reputed journals. We are really fortunate enough to have you, sir, with us as a resource person in this 2 week long faculty development program through online on research methodology and applied econometrics for social science organized by the Department of Business Administration, Assam University, Silchar, in collaboration with Vidyasagar University, West Bengal. So now I like to hand over it to you, sir. So the session is yours, sir.
Thank you very much. Thank you very much for this nice introduction. I hope I'm audible, right? Properly.
Yes, sir.
Okay, thank you very much. So let me just now start sharing my screen. So I came to know about this presentation just a couple of days ago. So I couldn't prepare a proper PPT for the entire lecture. So, but I prepared this write-up actually. This write-up can be shared also with other people if needed. So anyway, so can I start now?
Yes, sir. You may start.
Okay, thank you very much. So I'll give you a brief introduction of this data set of having both cross-sectional and time dimension, uh, because these kind of data sets are more and more used in research because it has some very because of this some desirable characteristics, basically I would say that makes this kind of data sets more and more in use in research. And there are 2 types of data sets having this cross-sectional time series variation. One data set we generally call is independently pooled cross sections data set. Is basically it is obtained by sampling randomly from a large population at different points of time. So you have a large population and at different point of time, often but not necessarily in years, you randomly select data. For example, in each year, we can draw random samples of wages, education, experience, etc. from population of working people. We can, let's say, also collect data, let's say, house price, cross section of houses, geographic location of houses. Okay, so this kind of data set is independently pooled data set, and this independently pooled cross section data are being used increasingly because it increases the number of observation in the analysis, producing more precise estimators and test statistics with more power. And it also helps doing different types of policy analysis. So this is basically, these are the major 2 reasons that why this kind of data set with the more time variation, one dimension is time variation, another dimension is cross-sectional variation, this type of data is more and more in use because of these two important reasons. First of all, it increases the number of observation for analysis, and as a result, it produces more precise estimators and test statistics with more power. And it also helps doing different types of policy analysis. This is exactly where we will more focus in this lecture, this 2 hours long lecture, because this kind of data set, it gives me this opportunity to ask for a more some special kind of policy analysis which cannot be done with only cross section data or time series data. So these are the two major reasons. First of all, more number of observation producing more precise estimators and test statistics with more power. And second, why this kind of data set is more in use in the research nowadays, because it also helps doing different kind of policy analysis. We will see later subsequently in this lecture, which cannot be done with data, with cross-section data and time series data. These independently pooled cross-section data are independent and not necessarily identically distributed, because the distribution of the collected variables might change over time. For example, you collect data of wage rate of a particular individual today, tomorrow, day after tomorrow, and so on and so forth. As the time progresses, the distribution of the wages can change over time, but it is independent. So, and most importantly, and we often take care of it by introducing dummy variables to the regression analysis. So even if the distribution of this collected variable changes over time, it is not identically distributed, it can be easily handled in the regression analysis simply by introducing some dummy variables. So it is called independently pooled cross section. So you simply collect data at regular time interval from a large population, not necessarily from the same person, same individual, same farm, same cities, not required. That is why it is independently pooled cross section. From a large population, you collect data from a randomly select data. Okay, so over here, I will give you one small example. Okay, with what kind of stuff can be done. First of all, this is important. The independently cross section data are independent but not necessarily identically distributed, because the distribution of the collected variable might change over time. We often take care of it by introducing dummy variables into the regression analysis. This is exactly the example, the 2 or 3 following example that we will give over here, that will actually take care policy analysis and how do we do it. First of all, let's say example one, women fertility over time. So general social survey collects data on women fertility. Is basically general social survey is basically for USA. Nowadays, is national health survey is going on in India. That also collects this kind of data for the Indian scenario. General survey data collects data on women fertility for even years. Using the data, we can run this kind of regression. So what is our objective over here? Our objective over here is whether the fertility of the woman has changed over the time. Over the time means I have data on woman fertility of 1974. I have data of woman fertility in 1976, 1978, 80, 82, and 84. So these 6 years, suppose I have data of woman fertility, and I collect this data and I wanted to check to what extent this woman fertility has changed over the time from 1974 to 1984, to what extent it has changed over time. Okay, so for that, I am running a regression. In the left-hand side, this is my dependent variable. For the ith individual and for the tth time period, I have collected the number of kids. So ith woman for the tth time period, what is the number of kids of that particular woman? That is basically my left-hand side variable. In the right-hand side variable, I have this constant term over here, beta 0, and I have some 6 dummy variables over here. So D74 is a dummy variable which takes a value 1 for the year 1974 and 0 otherwise. Similarly, D76 is basically a dummy variable which takes the value 1 for 1976 and 0 otherwise. Similarly, all other dummy variables are defined over here. This is, you see over here, as I said, that left-hand side variable kids IT, this is collected, is a independently pooled cross section. Its distribution, how does this distribution? They are independent, but their distribution might not be identically distributed. So what happens is the conditional mean of this distribution of kids might change over time. The conditional mean of this left hand side variable might change over time. How do I take care of that? By introducing this dummy variable. For example, for 1974, what is the conditional mean of the left hand side variable? Beta 0 plus delta 0. For 1976, what is the conditional variable of this left hand side variable? Beta 0 plus delta 1. So as long as this delta 0, delta 1, delta 2, dot, 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 delta 5 to delta 6, they're different. For each year, if the mean, the conditional mean of the left hand side variable changes, it can be taken care of. Okay, so this is exactly what I said, that it can be it might not be identically distributed because the distribution of the collected variable might change over time. We often take care of it by introducing dummy variables into the regression analysis. This is one example. If the mean of this left hand side variable, which is collected as independently pooled cross section, if the left hand side variables mean changes over the time, how do I take care of it? I simply introduce different dummy variables over here. So for 1972, the mean is beta 0. For 1974, the mean of left hand side variable is beta 0 plus delta 0. For 1976, it is beta 0 plus delta 1. So as long as delta 0, delta 1, delta 2, dot, 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 delta 6, they are statistically significant, we can actually take care of it if its distribution, if the conditional mean of the left hand side variable changes over the time. Okay, so over here, this is basically one way of handling the pooled cross section and its distribution changes over the time. My objective over here is to check whether over the time woman fertility has changed over the time or not. For that, I have used these dummy variables, and this xit over here, there are some other control variables. And what are these control variables we have taken for our analysis? Suppose educational level of the woman, age of the woman, age square of the woman, the race of the woman, in which category the woman belong, it is black or white. What is the geographical location of this woman? East, northern, west, town, urban, rural. All these kind of variables are basically taken care of in this variable xit, and uit is a random error term. So if the this is basically the simple regression that I will estimate by with simple OLS. So you see over here, left hand side variable is data collected is an independently pooled cross section, and all the variable in xit, education, age, all these kind of variables, let's say, this is also collected as independent pooled cross section, and I run a simple regression like this. And why I have introduced these dummy variables? Because all these dummy variables, because the mean of this left hand side variable might change over the time. And if I introduce this kind of dummy variable, that mean change can be taken care of. Okay. Any question till now? Any questions? Any clarification? Anybody? Okay. So I think till it is clear. So if I run this kind of regression, what I get is this. These year dummies 1982 and 1984, given that the 1982 and 1984 year dummies are individually quite significant. That means this delta 5 and delta 6, delta 5 and delta 6, they're individually quite significant, and they're significantly negative. So delta 5 is negative, its value coming out something like negative 0.522, and delta 6 is also negative, and its value is coming out something like negative 0.546. 5. So these two variables are highly significant, highly negatively significant. What does this mean? It basically means compared to 1972, the average number of kids of a woman in 1982 declines. Compared to 1972, which is basically my base year, compared to 1972, if I if I compare the number of kids of a woman 1972 and 1982, the number of kids, average number of kids in 1982 has declined. So how much is basically simply says 0.522 is basically something like almost 52%. There's an almost 52% decline in the woman fertility in 1982 compared to 1972. Similarly, delta 6 value is 5.545. So it basically simply says almost 55% decline in woman fertility has taken place in 1984 compared to 1972. Okay, so you see, since this kind of analysis that over the time to what extent the woman fertility has declined, this kind of analysis cannot be done with a single cross section. For that, for this kind of analysis, I need uh, time variation in the data. Otherwise, this kind of dummies cannot be created. And if this kind of dummies cannot be created, I cannot simply say, I cannot do this analysis if over the time woman fertility has declined or not. Interestingly, if all this delta 0, delta 1, delta 2, that means these are actually non-significant. But if I do for a joint significant testing of this all these dummy variable, they're actually coming highly significant with the F statistic 5.87 and V value is almost close to 0. What it basically says, yes, indeed, the distribution, the mean of the distribution of this woman fertility has changed over the time. If it has not been changed over the time, this joint significance of this dummy variable would have been 0. The null hypothesis would have been 0. So delta 0 equals to delta 1 equals to dot dot delta 6. That would have been accepted. But what I find that is not accepted. The F statistic highly significant. That means indeed the distribution of this left-hand side variable, the woman fertility, has changed over the time. And my results shows that mainly the change has taken place in 1982 and 1984, and it's a negative change. That woman fertility compared to 1972, in 1982 the woman fertility has declined 52%. Compared to 1972, the woman fertility in 1984 has declined almost like 55%. So this is one important result. Another important result is education. What I find, the education coefficient, which is over here in one of the control variable in this XIT vector. Okay, the education coefficient is coming something like negative 0.128. It basically simply says that compared to high school, it basically says average that with only high school education 0.518. So women are more education, have fewer children, and the estimate is very statistically significant. Other thing being equal, my result shows that 100 women with a college education will have about 51 fewer children on average than 100 women with only high school education. So high school education and college education, if I simply compare, it basically says women with the college education on an average has 51. The 100 women with college education on an average has 51 fewer children compared to 100 women with the high school education. So as the educational level of the women rises, their fertility rate is also declining. So these are very important results. First of all, over the time, the fertility rate of the woman is going down, one important point. And second, as the education level of the woman is rising, their fertility is going down. Okay, this is one example. Why I have given this one example? Because as I mentioned over here, the independently pooled cross-section data As the name suggests, they are independent, but their distribution might change over the time. There might not be identically distribution. How should I take care of that in my regression analysis? I take care of that in my regression analysis by introducing these dummy variables over here. If the distribution has not changed over the time, delta 0, delta 1, delta 2, dot, 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 delta 6, they would have been statistically non-significant and close to 0. My estimation shows that delta 5 and delta 6 are highly statistically significant negative. It basically says that as the time progresses, the fertility rate of the woman is going down. And when I test the joint significant of delta 0 to delta 6, they're coming out highly significant. It basically says that conditional mean of this left-hand side variable woman fertility is actually changing over the time. And another important result is over here. As the education level of the woman rises from high school to college education, on an average, high school women with high school education, 100 women with the high school education, if I compare their fertility with the 100 women with only college education, it basically says that if the college education women, they're actually having 551 fewer children on an average than the college education. So this is one important example that how this independently pool cross section data is allowing me to do this kind of policy analysis to what extent the woman fertility is changing over the time. This is one example that how should I handle it. Another example, let's say return to education and gender gap. For that, what I actually find out, what I'm actually trying to find out over here, that whether this wage rate in the left hand side variable, I have taken log of wage rate, log of real wage rate. So to what extent the difference in this log of wage rate changes from male to female over the time. This is exactly what I'm actually doing over here. So I've defined a dummy variable over here, D85. It basically says that it is taking the value 1 for the year 1985 and 0 for the year 1972. So 72 is my base year and 1985 is basically the year I'm trying to check to what extent this log and wage has changed over the time. So for that, I have taken this data, log of wage, again is an independently pooled cross section, randomly selected population over the time. I have collected data of this left-hand side wages, nominal wages. I deflated with the consumer price index. I got a real wage. This is my real log of wage in the left-hand side. In the right-hand side, this female is basically a dummy variable. So if a person is female, is taking a value 1. If a person is not female, male is basically taking a value 0. And this is my error term. This is an interaction term over here with this dummy variable over here. So what is happening when I do this kind of analysis, and also I have this all other control variables over the with me, XIT. What are these control variables is basically the education and experience square, whether the person is in the union or not. This is over here. My objective over here is to check the return to education and whether this return to education has changed for the female population from 1970 to 1985 in USA. Okay, so I run this regression over here. So what I found over here, you see for 1972, if I go for 1972, the average wages for all the people, male and female together, the average wages for 1972 is beta 0. But the average wages for 1985, taking male and female together, is basically beta 0 plus delta 0. This one. Okay, so if the average wage has changed over the time from 1970 to 1985, the delta 0 would have been significant. Okay, so first I can check the significant level of delta 0. If delta 0 is significant, I will say, yeah, the wage rate has changed over the time for US from 1970 to 1985. If delta 0 is negative, it's going down. If delta 0 is positive, is going up. As the time progresses, wages is growing up, delta 0 is positively significant, wages is going down for the entire population when delta 0 is negative. So I can check the significance level of the delta 0 using simple t statistic to check whether the wage is actually changing for male or female or entire population over the time or not. This is one thing I can do. And secondly, you see over here, for female, the average wage rate is basically for 19 for female, the average wage rate in 1972 is basically again beta 0, but for female it is beta 0 plus delta 0 plus delta 1. The average wage rate for female in 1985 is beta 0 plus delta 0 plus delta 1. So what I'll actually check, if delta 1 is not statistically significant, I will simply say nothing has happened. The wage rate for the woman, if I compare 1972 wage rate for woman and 1985 wage rate for woman, nothing has changed. In that case, I'll simply accept the null hypothesis delta 1 equals to 0. But if the null hypothesis is rejected and I have to accept this alternative hypothesis delta 1 positive, it basically simply says from 1972, if I compare 1985, the average wage of the female has increased. How do I test that? If my delta 1 is positively significant, then I will simply say the average wage of the female in 1985 has increased compared to 1972. So again, over here you see, I have only introduced a dummy variable that intercept change. Here, my objective is to change whether the female wage has changed over the time in the US or not. So what I find out, I actually introduce an interactive dummy over here. That interactive dummy, the coefficient of this interactive dummy will give me this result, whether the female wage has changed over the time or not. Okay, I can also introduce, suppose in XIT, as I said, I have a data of education. So I have this education data, let's say X, this is my education. And suppose I introduce another variable over here. Suppose I introduce another variable, D85. So suppose I introduce a variable like this, delta 2 multiplied by D85 multiplied by education. What I can actually check with this coefficient delta 2 over the time, whether the education level has any impact on the wage rate or not. Okay, in 1972, what is the impact of education on wages? It is my beta over here. Suppose this is my education only. In 1985, what is the impact of education on wage rate? That will be beta plus delta 2. If delta 2 is significant, then I will say, okay, education has impact on wage rate over the time. If delta 2 is absolutely non-significant, I will say nothing has changed. Whatever be the return of education in 1972 in US, the same return of education prevails in US in 1985 had delta 2 is non-significant. But if delta 2 is positively significant, it basically says if you are more educated compared to 1972, you are getting on an average higher wage in 1985. If delta 2 is negatively significant, I can simply say that as you get more educated, your average wage will fall down over the time. So this is how the interactive dummy will work in this. Again, in this example, I've introduced only the intercept dummy. In this example, according to my objective, I have introduced interactive dummy to check whether the return of education has changes and whether the gender gap and the education has any impact or not. Simply, I can do that because my data has this cross-sectional and time series variation both. It is allowing me to do this kind of policy analysis. And that is why in the beginning, I have mentioned that this this type of data, which has both cross-sectional and time series variation, they're more and more in use in the literature nowadays. And that is why you see India has also started collecting these kind of data set more and more. CMIE data, consumer pyramid data, and your, I think, IHDS, Indian Household Survey or something. It is done by NCAR along with Michigan State University. They are actually IESA's data, Indian uh, Expectation Survey of Household, done by RBI. This kind of data is basically again the same type of data, has cross-sectional variation as well as time series variation, because over the time India has also realized that if I want to do policy analysis, I need to collect this kind of data, and India has also started collecting this kind of data. So if you see these kind of examples, actually the interesting part over here is this type of data is collected for US for a long period of time, but India has just started collecting this kind of data. So there is a huge area which unexplored, because this kind of data that India is recently collecting, lot of analysis can be done with that. Keeping in mind, if you see these kind of examples more and more, you can actually apply this kind of examples with Indian data more with the Indian context, and you can do different kind of research paper. Okay. So again, any questions, any clarification till now? Okay. Another important thing, another important area where this kind of policy analysis can be done is basically example 3 that I've given over here, the difference in difference estimation. Very interesting analysis. So I'll give you two examples over here for difference in difference analysis, and then I'll say it's basically a natural. It basically more in use, more in natural experiment. Okay, so suppose this is one story that there was a rumor that a garbage incinerator will be built in northern Andover, Massachusetts in 1978. So northern Andover, Massachusetts, people suddenly started talking about there is an area where there's a garbage incinerator is going to be built. And actually the construction of this garbage incinerator began in 1981. The objective over here is there are certain households, they are closer to this garbage incinerator, whether their average price has gone down or gone up. Actually, whether their average price have gone down or not. So it's basically a garbage bin in your household or in your locality. Suddenly municipality has built a garbage bin. You just wanted to check the housing price closing to that garbage bin has gone down or not. This is basically your objective. Okay, so what you have collected data over here is housing price IT, housing price over here for the ith house at the tth time period, and you run this kind of regression. What kind of regression it is basically, as I said, the base year is 1972, the initial year, and the construction of this garbage incinerator over here has started in 1981. Okay, so my initial year is 1978. So this is my year 1. My year 2 is basically 1981. I define a dummy variable D81 such that this D81 is taking a value 1 for 1981 and 0 otherwise. This near is also a dummy variable. It basically says after the construction of this incinerator, household near to this incinerator is taking a value 1, otherwise 0. And I am actually introducing another dummy variable, the interactive dummy over here, D81 multiplied by near. So D81 is basically a simple dummy variable, which is taking a value 1 for 1981 and 0 otherwise. Near, this is also a dummy variable, is taking a value 1 for household near to the garbage bin, and this is an interactive dummy variable. Along with that, I can actually take all other variables in XIT, just like what is the locality of the house, what is the square foot of the house, what is the color of the house, whether there is a school near the household or not. All those kind of control variables are actually included over here, and UIT is the random error term. If I simply run this regression, it can be easily shown that estimated value of this delta 1 from this regression will actually give this. What is that? Is the average price of the household near to the garbage bin in 1981 minus the average price far away from the garbage bin of the household in 1981, their difference, minus the average price of the household near the garbage bin in 1978 minus average price of the household far away from the garbage bin in 1978. This is exactly what I need to check over here. So why do I need this kind of regression? I can if I have the data of household, I can simply calculate the average of this housing price, which is near to the garbage bin in 1981. I can also calculate the average of the housing price, which is far away from the house from the garbage bin in 1981. Similarly, I can calculate the average of this. I can calculate the average of this. I can simply take this difference. I can calculate that, but if I do not do this kind of regression, I cannot have the standard error of this variable, of this coefficient, and I cannot test its significance. That is why I need to find out this measure from the regression analysis. This is exactly what a difference in difference estimator does. So this is first difference. This is another difference. It is the difference of the two difference. That is why it is called a difference in difference estimation. As I said again, I can, if I have the data of housing price, all these variable, the average housing price in 1981, average housing price in 1978 for two types of houses can be easily calculated. And I can calculate this right hand side very easily. But unless and until I obtain this right hand side variable from a regression analysis, I cannot do their significance testing. Because now if I run this regression, I get the estimated value of delta 1 hat, and I'll also get the standard error. From there, I can get the t statistic. If this delta 1 hat is statistically significant, I can say yes. Once the garbage incinerator has been built, the houses, the average price of the houses near the garbage bin has actually gone down. Okay, if my delta 1 hat is negative and is highly statistically significant, I can actually say the average price of these houses near the garbage bin has actually gone down. Okay, this is another important thing. And let's say this is one example. Another example could be, suppose this is basically is done nowadays quite regularly, this what is called your this RCT, randomized control trial. Let's say you find out a household, you give a certain household of a locality some mosquito net, and certain household of the locality you do not give the mosquito net, and you can simply check whether the distribution of mosquito nets has a significant impact on this malaria incidence or not. Similarly, nowadays governments are giving cycles actually, okay, to check, especially to the to female, to increase their participation in school. Okay, so you have certain locality, certain population, let's say, and you identify certain population, some certain subset of that population, and you give cycles to them. Rest of the population you do not give cycle, and simply you can check whether their educational attainment with the cycle has increased or not. Again, you have to do the same thing, okay, over here. So just simply a standard over here is basically, suppose in period 1 and period 2, in the period 1 all the households are identical, that means all the people, they do not have cycles. In period 2, some people who are basically called the treatment group T, they had the cycle, and the rest of the people who call the control group, they do not have the cycle. And I can simply run this kind of regression. Suppose my left hand side, my educational attainment, beta 0 is a constant, D2 is basically a dummy variable, which is taking a value 1 for the second time period after distribution of the cycle, and otherwise 0. DT is basically a dummy for the treatment group who got the cycle at the period 2, it taking a value 1, otherwise 0, and this is the interactive term over here. I simply run the regression, I get the value of delta 1 hat, and I'll simply check the significance of the delta 1 hat. If delta 1 hat is positively highly significant, I will say yes, the cycle distribution has impact on the educational attainment over here. Okay, so this is exactly what difference in difference estimator does, and it has a huge application, in randomized control trial. This randomized control trial, as you all know, it has been done by regularly by pharmaceutical companies to test the impact of medicine. But nowadays, after this Nobel Award by Esther Duflo and Abhijit Banerjee, everybody is nowadays now it's doing is randomized control trial analysis. Okay, so ultimately the basics of randomized control trial is this difference in difference estimator. You just simply has to do this kind of regression analysis and to check whether the significance of this interactive dummy, that is basically your main concern over here, whether that is significant positively or negatively or not. So what it basically does is basically in any kind of experiment like this, again you have a independently pooled cross section data over the time. You need data for at least 2 period, and then you have you define this kind of dummy variable for treatment group, for control group, 2 period, and you do this kind of analysis and run the significant test of this delta 1 hat. Okay, so this is basically another important aspect of this data that allow you to do policy analysis. Okay, so difference in difference estimation. So this is basically the 3 examples that I have given over here. I have started with this data set. One type of data set is it has cross-sectional variation, time series variation, and independently pooled cross section. I said that more in use in the research. Why? Because we do some kind of policy analysis with that, which cannot be done with the cross section data only. And we have given this example that over here, whether the fertility of the woman has changed over the year or not, whether the educate return to education of has changed over the year or not, whether the gender difference has any impact on the wages or not, again over the time. Okay, and this cannot be done with the cross section data. And as I said, since the independent obviously fine is independent, it might not be identically distributed. How do I take care of that? By simply introducing these dummy variables. If I introduce this intercept dummy, is basically simply said, okay, the distribution, the mean of the distribution is changing, I'm allowing to change over here. Okay, so this is one thing. And difference in difference estimation, this can also be done only with the data with both time series variation and the cross section variation. So this kind of policy analysis, which cannot be initially done with the only cross section data, now can be done with this data with both kind of variation, time series and cross sectional variations can be done. So that is why this kind of data are more and more in use. This kind of data being collected in US for a long period of time, but after realizing the importance of this data, India has also started collecting this kind of data more and more. So this area is absolutely completely unexplored. New data set, you have this statistical technique, econometric technique. India is giving you new data set. You can actually utilize it for different kind of research, for different kind of papers. Okay, that people are using this. So this is independently pooled cross section. One type of data, as I said, independently pooled cross section, where I simply collect data at different time interval, but not necessarily from the same individual or same state. This is exactly where the panel data differs. Panel data is basically, it is collected initially with the randomly, I select certain population, from there I collect data, but I collect the same data from the same population, same individual, same cities, same town at regular interval. That is panel. This is exactly what I have mentioned over here. This is my panel over here. Panel data or longitudinal data. Data is obtained from the same individual, farm, cities at regular interval of time. For example, we can collect data on wages, hours, education from the same group of initially randomly selected people. So at the first year, you wanted to collect, that group is randomly selected. But second year, third year, fourth year, so on and so forth, you collect the identical data from the same population only. That is your panel. And this is exactly where it is actually different over here. You collect data over here, but not from the same population, independently pooled cross section. You collect data over the time, but from the same population, as if you are tracking one individual over the time, one cities over the time, one farm over the time. That is basically your longitudinal data or panel data. And what is important over here, unlike over here, as I said over here, the distribution are independent but not identical. In the panel data, that distribution might not be independent as well. Because suppose you have collected data of wages of a ith individual at the time period t, and alpha I, suppose it is the unobserved factor, which is called the ability of the individual. Okay, so if ability of a particular individual can affect the wage rate of the individual in 1971, the same ability of that individual can affect the wage rate of the individual in 1980 as well. So because of the presence of this unobserved component ability, the data that you collect over the time, the panel, they might be correlated with each other. And this is exactly the major importance of this panel data, to identify this unobserved component alpha I over here. This is a typical panel estimation, panel equation over here. YIT equals to beta transpose XIT plus alpha I plus UIT. XIT is basically all the control variables. Alpha I is the unobserved factor, unobserved individual specific factor. So it can be your ability, if it is a farm, the geographical location of the farm. Okay, so this kind of factors over here, and this is the idiosyncratic factors. So this is a absolutely simplest possible panel, and which is I call the fixed effect panel. The question is, how should I estimate this panel? There are two ways this panel can be estimated initially. Actually, three possible ways. First of all, I can do a simply first difference. YIT minus YIT minus 1 equals to beta XIT minus XIT minus 1 plus UIT minus UIT minus 1. I can simply run this regression. Absolutely possible. Or what I can do, I can run this regression. YIT minus YI bar equals to beta XIT minus XI bar plus UIT minus UI bar. This is called the fixed effect estimate. This is called the first difference estimate. I can do that. Both estimates are valid as long as you see over here, if my UIT is uncorrelated with the XIT and XIT minus 1, UIT minus 1 is uncorrelated with the XIT and XIT minus 1, I can simply run this regression. I have no problem. I'm going to get the absolutely consistent estimate. I do not have any problem of endogeneity. The same thing applies over here. As long as my UIT minus UI bar is uncorrelated with the XIT minus XI bar, I have a consistent estimate. So if my time period is 2, it can be shown mathematically this first difference estimate and this fixed effect estimates are actually identical. But if my time period is more than 2, if you ask me the question, if I have a panel, I cannot do for this pooled estimation, because if I do for a pooled estimation, this error term, this alpha I and this XIT, suppose my education and alpha I, this is my ability, they can be correlated. So pooled estimation is not possible. I have to eliminate this alpha I for my estimation. How do I do that? I can take a first difference, or I can do this kind of operation over here. In both the cases, alpha I is removed. And if my error terms are uncorrelated with the control variable, I have a consistent estimate. Both FD and FE consistent. FD is identical with FE if I have a 2 time period data. But if my data has more than 2 time period, if you ask me that whether I go for a first difference estimation or a fixed effect estimation, very difficult to say. What I can actually say is that if my error term, this UIT, is basically very highly correlated. Let's say it's a random walk process, the correlation is 1. Then this is basically UIT minus UIT minus 1 is basically a white noise. In that case, so if it is very highly positively correlated, it says that, okay, you go for this first difference estimate. Otherwise, you go for this fixed effects estimate. Secondly, if my control variable, if some of the control variables has your this what is called your estimation error, okay, classical estimation error, then it's better to go for a fixed effect estimate than the first difference estimate. My fixed effect estimate is highly sensitive to this, the normality of error term, your heteroscedasticity of the error term and all those, but my first difference estimate is not. So Sometime first difference estimate is better, sometime fixed effect estimate is better. It's very difficult to say that which model I should estimate, whether go for first difference estimate or fixed effect estimate or not. So the suggestion is basically what the econometrician does. They actually give you actually estimate both of them and try to find out the best fitted model and try to explain that why the difference is actually taking place. Okay, so this is one thing. So this is, I think we all know this, the standard, absolutely standard fixed effect model. Okay, suppose right hand side is basically my wages of the I8 individual or T8 time period. Right hand side my educations and etc. XIT. Alpha I is basically my unobserved ability, and random error term is over here. Alpha YIT can be profit of a firm. XIT is basically the profit of a firm, depends on different kind of stuff. Alpha I is basically the profit of a firm. It is unobserved factor. Let's say the ability of the manager, that is affecting my profit of the firm, alpha I, which captured in alpha I. Okay. But if I go for a simple estimation over here, let's say if a person is highly educated, because it is its ability, the initial ability is very high. So this education and the ability can be correlated. If that happen, I have a inconsistent estimate. So I have to remove this alpha I for the estimation. How can I do that? I can do for a first difference, I can go for a fixed effect. First difference, fixed effects are identical for t equals to 2. But t greater than equals to 2, sometimes fixed effect is better, sometimes first difference is better. I really do not know where it is, what to choose. So the suggestion is to go for both of them and then go for the estimation. Okay, again, any questions, any clarification? Okay, so then what I will do, I'll share a new screen over here. So if I go for it, is this screen visible? This new screen is visible.
Yes, sir.
It is visible, right? So this is exactly what I said. This pool regression, fixed effect that I've already mentioned over here. Other than fixed effect, there is another estimation that I have mentioned over here, is basically the random effect model. So this is my equation again. Beta xit plus alpha I plus uit is the composite error term, and this is basically, you see over here, if alpha I and my xit is correlated, I cannot simply go for the estimation of equation number 4, inconsistent estimate. So for the random effect estimate, we simply assume this alpha I and this xit is uncorrelated, alongside certain assumptions about these other correlations. My expectation of this error term is 0, variance of error term is sigma u square. They are serially uncorrelated UIT and UIS. XIT and UIT is 0. Alpha I and UIT, as I said, this assumption is very important. My alpha I and XIT, they are uncorrelated. If they are correlated, I have to go for this fixed effect estimate or first difference estimate. But if they're uncorrelated, I can go for this random effect estimate. I am not going in detail of this random effect estimate over here. It's basically a generalized least square estimate, because I get certain kind of variance covariance matrix over here. I have not written it over here, so I have written. So you go for this, you define this kind of variable yit minus theta yi bar, xit minus theta xi bar, theta is something like this, and you regress. What you get is basically a random effect estimate. I'm not going in detail technicalities over here, but interesting thing that is very important over here, that how do I choose a fixed effect estimate or random effect estimate? Okay, first I discussed that how do I choose a fixed effect estimate, a first difference estimate. As I said, there are some condition where the fixed effect is better, some condition the first difference is better, and most of the time econometrician does not know which is the better one. But over here, when you choose for a fixed effect or random effect, there is a test. There is a specific test called the Hausman specification test. The null hypothesis of this test is xit and alpha I it is 0, and the alternative is xit and alpha I is not equals to 0. So you simply run this regression with fixed effect and random effect. You get this estimated value of the coefficient, their variance covariance matrix, and over here it basically follows a chi-square distribution. What it basically says, if my alpha I and xit, they are uncorrelated. Suppose my null hypothesis is accepted. In that case, I can go for fixed effect, random effect both, but random effect is more efficient. So both FE and RE is consistent, but random effect is more efficient. But if my null hypothesis is rejected, that means my individual ability and the one of the control variable is correlated. Suppose my individual ability over here and my educational qualification is one of the control variable. They can be correlated. If they are correlated, I cannot go for a fixed effect estimate. The only fixed effect estimate can be done. I cannot go for a random effect estimate. Sorry. So if they're correlated, otherwise I'm going to have an inconsistent estimate. This is exactly what Houseman's specification test does. Okay, so null hypothesis is this is equals to 0. Alternative, this is equals to 0. So if I have to accept this null hypothesis, both FE and RE can be estimated consistently, but it can be shown that random effect model is more efficient. It has lower variance. But if they are correlated somehow, the fixed effect is completely gone. Sorry, the random effect is completely gone because that is a inconsistent estimate. I only have to go for these fixed effect estimates over here. Okay, so this is the important test. So if you have a panel data in your hand and you have to go for an estimation, you have generally have three choices. If it's a static panel, is basically either you go for a fixed effect estimate, or you go for a first difference estimate, and you go for this random effect estimate. Choosing random effect and fixed effect, between choosing random effect and fixed effect, that is a test, Houseman specification test. It can actually say that whether you go for a fixed effect estimate or random effect estimate. But if you really need to choose between a first difference estimate or a fixed effect estimate, difficult. There is a distributional problem, there is a measurement error problem. In fact, there is no problem with the consistency. In fact, so both the estimates are consistent as long as block exogenity assumptions are satisfied. But other problems are there. If the error terms are serially correlated, what kind of serial correlation does it have? Positive, highly positive, negative, all depending, all this kind of stuff, you have to go for this estimation. So that is why generally the econometricians suggest that, okay, if it is the case, then you go for a estimation both first difference and fixed effect. Try to find out their difference and try to explain their difference and why they are different. Okay, so this is basically a standard static fixed effect case. So the two types of data generally, I can have this individual independently pooled cross section. They are more and more in use because it has certain desirable properties that is better for the policy analysis. And another one is absolutely panel for same individual or same cities or same farm you are tracking over the time. In that case, what happened? That individual the cross-sectional heterogeneity comes into picture, and that is why the data can be correlated. In that case, that individual heterogeneity has to be handled, and that is also handled by using a simple dummy variable. And but pooled estimation in that case cannot be done, because in that can be inconsistent if this individual heterogeneity is correlated with xit on the control variable. Either you have to go for a first different, fixed effect, random effect. What to choose? Fixed effect, random effect. To choose what to choose, go for a Houseman specification test. But to choose between this first difference or fixed effect, there is absolutely no general unanimous suggestions. Okay, so this is basically my lecture all about. Okay, any questions, any clarification? How do I go to this full screen over here? Any questions, any clarification? Okay, this is one thing I can see. The fixed effect estimator, how should, yeah, good evening, good evening. Fixed effect estimator is sensitive to normality of errors and the heterogeneity. What does it actually mean? It basically means that, very simply spoken, central limit theorem does not apply in the two cases in the panel data estimation. First of all, if your number of cross-sectional unit is small, but the time series is large, that is n small, capital T is large, in that case, this central limit theorem does not apply. And another case with the central limit theorem does not apply if the errors are not normal. So that is why they say the fixed effect estimator are highly sensitive to normality. You suggest any basic book resource? Yeah, if you go for more intuitive application of this kind of data, I would suggest you go for this Introductory Econometrics, a modern approach by Jeffrey M. Ulrich. And if you want to go for even more technical, then you go for this Jeffrey M. Ulrich. They has a higher level book. Is basically, I think, Econometrics for cross section and panel data. I think that is the name of the book. You can go for that. You can go for Baltagi. Baltagi has a nice book for panel data analysis. So these two books are good. And obviously you can have green always with you, because that's basically the basic Bible that we econometrician always go for. This green, first we read green, then we go for different kind of books over here. But these two books of Ulrich is extremely good, especially this introductory econometrics book is extremely intuitive, not very technical, but you'll understand the basics over here very clearly. Is stationarity testing required for panel data analysis, both short and long panel? Stationarity of not the stationarity of the data, but the correlation of the error term. As I said, that if your error term is very highly correlated, it is better to go for a first difference estimate than the fixed effect estimate. So yes, you can actually go for checking this serial correlation of the error term. Okay, sir, when panel data is applicable in case of social science research, especially education? I have given one example, right, that to extend that whether this educational, the return to education, whether education has impact on wage rate or not. Okay, this is one example that I have given. How to deal with the serial correlation problem in the case of panel data. If you have a serial correlation, that's absolutely standard case that you go for either Cochrane-Orca transformation or Praise-Winston transformation. You get this variance covariance matrix, and you go for a GLS estimate. Again, same thing. If you have a heteroscedasticity, just like the random effect model. In the random effect model, the error term is heteroscedastic. What we do is basically we find out, estimate this variance covariance matrix and go for a feasible GLS analysis. So if you have a error term which is either heteroscedastic or there's a serial correlation, the standard method applies, which you have learned before. Ultimately, your objective is to find out a error, a variance covariance matrix, which is an identity matrix. So you go for the transformation. If it's a serial correlation, go for this Praise-Winston transformation. If it's a heteroscedasticity, do the relevant thing which you have learned before. The same applies. Anything else? Where to write? Over here. Jeffrey M. Ulrich. Ulrich has two books. One is Introductory Econometrics, more intuitive, less technical, and a book for another book is basically advanced level, which is more technical. Another one is from Baltagi. Yeah, you can go for that. Baltagi is absolutely specifically for the panel data analysis. Baltagi's book. Another one apart from Baltagi, you can actually see, as I said, Jeffrey and Ulrich. You can actually see also Green. Anything else? Any questions? Any clarifications?
If you have any question, you may ask. Dear participants.
So they are chatting with me. Some people, they are writing in the chat box. But if anybody want to ask any question, interact. No, I
There is
cannot.
no question. Yes, sir.
I can you
So,
show a practical example over analytical software? No, I cannot do that. I don't do that. Teaching software is absolutely a person's own thing. You have to learn your own software skill. I also do not have softwares in my computer. So, but I have given you examples of some estimations, actually, what I have done with the data. But I do not have those files of estimation files. This is absolutely standard model. You can go for Stata, SPSS, even EVUs can do it. Time span of the panel data. As I said, it should be large N, small t. Then all the statistical inferences and everything which has been developed till now applicable. That how large N, how small t, nobody knows.
Thank you, sir, for your nice deliberation and interaction
Thank you
regarding
very
the
much.
panel data
Actually,
analysis.
had I known about this lecture, let's say at least a more couple of days more back, I would
Yes,
have
yes, sir.
prepared
Yes,
more. So I came to know at something like at 10 o'clock in Monday. So that is why. Otherwise, I could have given a better lecture. Anyway, so anybody want to chat with me? Let's say my email is available, so you can email me. I'll obviously reply back.
yes, yes, sir. So, with this, I now request Joyita to kindly offer a formal vote of thanks to our honorable resource person and other present here. Joyita, hello. Joyita, hello, hello.
Professor Shao is absolutely fine. I have really enjoyed delivering this lecture. So
Yes, yes,
thank you for inviting me, and thank you for all the participants who listen to this lecture. If anybody has any question after this, you can email me. I will reply back. Okay. Oh,
okay.
Thank you, sir.
okay. Yeah. Thank you very much. Thank you
Thank
to
you, sir.
everybody.
Thank you, sir.
Thank
Can
you.
you offer
Thank
the
you.
vote of thanks for a few minutes?
Yeah.
Fatima ji,
Sir?
can you offer the vote of thanks? Just few words for sir. Yeah, Jaita is there. She will give. Jaita, please.
Thank you, sir.
Thank you very much. Thank you very much for inviting me.
And thank you so much, Dr. Dipjyoti Chaudhary sir, for giving me this opportunity to deliver vote of thanks for today's session. Now that we have come to the end of this session, I would like to offer my vote of thanks to a resource person, Dr. Siddhartha Chattopadhyay sir, for today's session, for enlightening us with his immense knowledge and for sharing his valuable inputs. All the important technical part which sir has taught us today will definitely add value to our research work in the long run. I would also like to extend my gratitude to Dr. Dipjyoti Chaudhary sir, Senior Assistant Professor, Assam University, for organizing such an informative session for all of us. I would also like to thank all the organizing members from Vidyasagar University and all backend coordinators for their support for making this event successful. Finally, a big thank you to all the participants who are present here today, because without you all, it wouldn't have been possible to make this session a successful one. Now, I would like to end this session with a quote by MC Moricom: "Don't give up, as there is always a next time." Having said that, I would like to end the session. Till then, stay safe, stay healthy. Thank you, sir. Over to you, sir.
Thank you very much. Again, thank you for inviting me. Uh, Thank you very much. Thank you very much. Thank you. Good night.
Thanks, sir.
Thank you, sir.
Thank you, sir.
So it's a day. So we are meeting again tomorrow, the same time, 4 p.m. Thank you.
Deepjyoti, sir.
Yes, any queries, please?
Yes, sir. So just wanted to ask, can we submit our paper till 19th or 18th?
I said a number of times that you can take 2 or 3 more days. Like when you submit, you will get the certificate.
4 more days. Okay, sir. So
No
the
issue.
time we submit, when we'll get a certificate? I mean, after how many days of
No,
submission?
as soon as you submit, you will get the certificate.
Okay, sir. Thank you.
Any other queries from any other person regarding the paper submission?
Thank
Any
you, sir.
issues? Okay, thank you.